Good morning, everybody. Today's lecture will be followed on Monday by our second midterm, same format as the previous midterm, and everything included in today's lecture, as well as the assignments, will be covered by the test. So please do some good studying over the weekend. I will go directly towards the share screen, and our ambition today is to deal with a situation where the neutrons are interacting with a material that is multiplying, and the terminology in the nuclear field behave because neutrons behave in the same way as bacteria or viruses. Is that we have an analogy between the behavior of neutrons as well as neutrons. So the same equations that are used to describe the multiplication of bacteria is used in when we deal with the interaction of neutrons with matter in general. And here we specify that today that we are going to deal with how neutrons diffuse in, well, we've done it already in non-multiplying media. That would be shield problem. Today, we are going to deal with the interaction of neutrons with multiplying media. The equation that comes out from the non-multiplying media looks like a source problem. It's almost like a linear system of equations if you think about an operator. In the multiplying media, which constitutes one group reactor theory, you find that the formulation of the equation, because the source of neutron now depends on the flux that the fission reaction is creating, it is not a source problem anymore mathematically, but it is an eigenvalue problem. And so you'll find that the treatment mathematically has to be different. But notice the analogy between the fields of bacterial populations as well as neutrons. The bacteria can divide by the process of fission. So we talk about fission reactions in the field of nuclear energy. Bacteria also can fuse together, or cells can fuse together. So we have the process of fusion. And today we are going to introduce the concept of a multiplication factor. And you could see immediately the analogy in that bacteria multiply and the population of bacteria can grow. So does a population of neutrons can grow and also can die off. So when we deal with multiplying media, we are treating the theory of how reactors functions in general, and you become privy as a group of young future engineers with a secret of the nuclear age. It's as simple as that idea of reactor theory. To simplify matters, and we are going to use one group of neutrons. We are going initially to consider that we have only neutrons that are thermal, which is the basis of designing existing light water reactors when the neutrons are in thermal equilibrium with the medium. All right, so one group means that they have one energy group, that all the neutrons have the same energy. Later on, we can generalize it to multi-groups, where you consider some neutrons that are fast, some neutrons that are intermediate in energy, and some neutrons that are thermal in energy. Again, we are going to consider the Helmholtz equation, the steady state solution that we used with the case for non-multiplying media, except that we notice that the analogy to the simple harmonic oscillator has on the right-hand side of the equation a negative sign rather than the positive sign that we got in the previous case of a non-multiplying medium. Hence, the solution is going to be somehow similar to the oscillating harmonic mechanical or electrical oscillator, and that the solution is going to be harmonic, meaning it's going to be oscillatory in terms of cosine and sine functions. However, it is not a solution as a function of time like the simple harmonic oscillator, but it will be a solution as a function of space. So it will determine the spatial distribution of the fission process, hence how the power production is occurring. Again, I remind you of the Helmholtz equation. We got it by a simple balance of the neutrons produced per unit time, d partial n by dt, being equal to the neutrons produced by the fission process minus the neutrons lost by the absorption per unit volume per unit time, minus the leakage from the surface. And in that case, the system, if it is it's just critical, meaning that the chain reaction is self-sustaining, it would be the steady state solution. So dn partial by dt should be equal to 0, which means what? It means that the losses are equal to the gain. So we derive equations in mathematical physics and engineering and economics in all the fields of science and engineering by carrying out some kind of balance equation. So that balance equation describes the behavior of the neutrons. The diffusion equation, as written earlier, was written in that form, and we are going to consider the steady state solution. So dn partial by dt is equal to 0. S is the source of neutrons, minus sigma phi the flux, sigma sub a, the absorption cross section. This would be the absorption rate density. We said that should be minus minus. Remember, this term here is a plus. It has it's a loss term because that represents the leakage from the surface of the reacting medium. But when we introduce Fick's law, we get another negative sign. So it's a plus plus that could be misleading because it's really a loss term with a second negative sign from Fick's law. D is a diffusion coefficient, and we have here the del square phi, the flux. Remember that the flux is a scalar quantity, very much like temperature, like voltage, like hydraulic head. It adds up in a scalar way. I gave you a problem along this line. When you deal with the flux, it adds up in a scalar way. When you take its derivative, the gradient of the flux in Fick's law, it becomes a vectorial quantity. The same way that if you take the derivative of the temperature, the gradient of the temperature, in that case, you get the heat flux, a vectorial quantity. When you take the derivative of the voltage, a scalar quantity, you get the electric field. And so let's keep that in mind, that there is an analogy between our solution for the neutron flux, how neutrons interact with matter, with other fields of engineering and science. All right, that diffusion coefficient has to be described. So we describe it in general as 1/3 the scattering mean free pass. That's one way of describing it. The scattering mean free pass is 1 over the macroscopic scattering cross section. If you want to introduce some detail from the more advanced theory of it's called transport theory, we take into account, as we mentioned in a previous chapter, the average cosine of the scattering angle. So that transforms that diffusion coefficient into a format that is described by what we call the macroscopic transport cross section, which is nothing than the sigma scattering, the macroscopic scattering cross section here, but modified by the cosine of the angle, the average cosine of the angle of scattering. And mu sub 0 has a very simple expression from the collision theory, the mechanics of the interaction of neutrons with materials. It's 2 divided into 3a. Capital A is the mass number of the isotope that we are considering. And in that case, a modification of the diffusion coefficient is that it is 1/3 the transport mean free pass, where the transport mean free pass is equal to the 1 over the transport macroscopic cross section. And this in terms is described as a modification of the macroscopic scattering cross section by 1 minus mu sub 0. I'm describing this because we are going to use it later on for an example and in some computation. So remember that mu sub 0, the average of the cosine angle of the scattering, is 2 divided into 3a. Very simple description right there. All right, now we have a multiplying system. The neutrons now interact with uranium-235. They fission it, and the multiplication comes in here from the fact that each fission is going to produce, on the average, 2 to 3 neutrons. And one of them could escape from the system, another one can be absorbed in the system, and we would have one left to keep the chain reaction of the multiplication process continuing. So we describe the fissioning process in the same way as I suggested in analogy to bacteria, by a multiplication factor. K is a symbol for the multiplication factor. This would be the neutrons produced in a current fission generation. Look, we are using generation here again in analogy to bacterial populations, divided into the neutrons absorbed in the previous fission generation. We identify that multiplication factor with the infinity symbol here, because that applies to an infinitely sized medium, very large medium without boundaries. We will correct that later on, because reactors, of course, have a finite dimension, and we'll designate it later as the effective multiplication factor. But for the time being, if I have an infinitely large medium, the neutrons behave like bacteria. They multiply through the fission process. The fission process occurs in 4 different steps, and that infinite multiplication factor is described by 4 factors, and that is a very simple formula to try to remember here, is designated as a 4-factor formula. The first term here, eta, represents the regeneration factor. This is the number of neutrons that are generated from one single fission effect by a neutron absorbed in the fuel. Some neutrons can cause fissions as fast neutrons, even though we are considering primarily thermalized neutrons, neutrons in thermal equilibrium with a moderator medium. So maybe we can get 5% extra fissions from fast neutrons. So we account for this by a factor called the fast fission factor. Now, in the chapter on neutron interactions, we discovered that the neutrons are born in fission at about 2 million electron volt of energy, and they have to slow down in the mixture of the moderating medium and the fuel to thermal energies of 0.025 electron volt, or the KT neutrons. And they have to escape being absorbed in the resonances, because if they are absorbed in the resonances, they form with uranium-238, say, or uranium-235, another isotope like uranium-236 or plutonium-239. In that case, they are not available for the fission process. So we designate that factor as the resonance escape probability. And then here the neutrons now are thermal, and they encounter a mixture of the fuel plus the moderator plus the coolant plus the control rods. All the materials that form the fissioning system. So in that case, a fraction of them only, or is used in the fission process, and we describe this as a fuel utilization factor. This formula is the basis of writing a criticality equation or a balance equation for the fissioning process, and it's named as the 4-factor formula. Try to remember it if you please. Let us expand on this 4 factors in the multiplication formula, it's very easy to think about the fuel utilization factors, almost like an efficiency here. This is the rate of neutron absorption in the fuel divided by the total rate of neutron absorption in the whole mixture in the reactor core, the fuel, the moderator, the structure, the control rods, everything else. So what is the rate of absorption? It's the neutron flux multiplied into the macroscopic absorption cross-section divided by, again, the total rate of neutron absorption in the fuel plus in the moderator plus in the structure and so on. For simplification, we can cancel out the flux if it's a homogeneous medium, and it becomes basically the absorptions in the fuel, the macroscopic absorption in the fuel divided into the macroscopic absorption in the fuel, the moderator, and the structure, control rods, and everything else in the reactor. All right, so that's how we can calculate that fuel utilization factor. The regeneration factor designated as eta, the Greek eta here, is really the neutron produced from efficient process relative to the neutron absorbed in the fuel. And we can write this in terms of nu here. Nu is the average neutrons produced per fission event, 2 to 3 on the average. So let's say it's about 2.5 for uranium 235 multiplied into the fission rate, sigma sub f phi, the flux, divided into the absorption, macroscopic absorption cross-section in the fuel. So in that case, we can also make the approximation that phi and phi cancel out. The absorptions in the fuel is equal to the fission macroscopic cross-section in the fuel plus the neutron captures, where a neutron is absorbed and the gamma photon is emitted. We can expand the macroscopic fission cross-section as capital N, the number density of the fuel, multiplied into the microscopic fission cross-section, divided again by that factor. And then again, we have to introduce capital N here for the radiative captures as capital N sigma sub gamma. I'll stop the share for a second and go back and see if anybody needs to be admitted to the all right, I'll go back to the screen share here. Nobody needs to be admitted, so share again. I hope it's recording. All right, so that is the regeneration factor. Then the N cancel, and then it becomes something that we can calculate very easily if we know the average number of neutrons produced in a fission event and multiplied into the ratio of the fission, microscopic fission cross-section to the microscopic fission cross-section plus the radiative capture cross-section in general. Now, usually it's easier to consider the ratio of the radiative captures to the fissions. We designate that factor by the factor alpha, and we can rewrite the form for the regeneration factor as nu, the average number produced per fission event divided by 1 plus alpha. All right, so this is the way that we can calculate that infinite number multiplication factor, a medium that is infinite in size. We use this to define in the Helmholtz equation what is the source term. The source term, unlike the case of the non-multiplying medium, now depends on the solution itself, on phi, the flux. It depends on the absorption rate of the neutrons in the fuel multiplied into that multiplication factor that we defined earlier. And if that multiplication factor K infinity is larger than 1, then the system will start growing, like a bacterial population will start growing. And if it's less than 1, the bacterial population or the neutron population, the source in our case, will also decrease, and you shut down your reactor, or you cannot have a self-sustained chain reaction. So the source term now in the Helmholtz equation is not a constant, like what we have done in the previous chapter in the non-multiplying system, but it is the absorption rate of the neutrons in the fuel multiplied into that multiplication factor, depending on what value it is for an infinite medium. And if you notice here from the absorption cross-section definitions of the fuel utilization factor and the regeneration factor, it depends on the compositions of the materials. What is the fraction of the uranium-235 in the fuel, the enrichment in that case. It depends on the moderator to fuel ratio, how much moderator we have relative to the number of fission atoms that we have. And in that case, this infinite medium multiplication factor multiplied by the absorption rate gives us fast neutrons. But those neutrons are that cause the fission in thermal reactors, the one group theory that we're dealing with, have to escape the region of, they have to escape from the region of high energy to the region of low energy. So in that case, you find that we have to identify the source by modifying the infinite medium multiplication factor by L sub f. L sub f, as we'll see later, is what we are going to call the fast non-leakage probability from the device. So in that case, it is not an infinite multiplication factor anymore. We turn it into, we identify here that we take into account, in fact, the size of the reactor by considering that leakage can happen from the surface of the reactor. So the source term becomes then a function of the solution itself. As you could see here, it is not a constant when we deal with a multiplying medium. And that is, in essence, the difference between a multiplying medium as we are dealing with today and the previous chapter when it was a constant source. So it was a matter in the previous chapter of shielding against the neutrons, whereas here we are trying now to keep the chain reaction sustained in a controlled manner. All right, so we go back to the Helmholtz equation, and if we take the transient one, again, just because that is really the general case, you find that the source term now is that K infinity L sub f sigma absorption, the macroscopic absorption cross-section multiplied into the flux. Now that is d partial n by dt, and we can express this in terms of the flux. The flux is nv. So in that case, if I take nv and divide into v here, I can substitute for the flux. So the Helmholtz equation is 1 over v d partial d by dt. The leakage term, remember, this is a negative term, negative sign because it's a loss term, and another negative sign because of Fick's law, so it becomes a positive, but it is the leakage term. It is how the neutrons are leaking from the surface of the reactor, minus the absorption rate, plus the source term coming from the fission process. Let us simply take this two parts of the equation and divide into the speed of the neutrons, v here, divide by sigma sub a, which is the macroscopic absorption cross-section. So in that case, you end up with d divided into sigma a. Now d has units of centimeters, and sigma sub a has units of centimeter minus 1. So they combine to become a centimeter squared, and that quantity has a physical meaning because it has now the units of an area. And if you take the square root of that area, it is a distance. And this is what we call the diffusion lengths. And the square of the diffusion lengths is L squared. So it has a physical meaning here. The physical meaning is that this is the distance traveled by the neutron on average between the time it is born to the time where it is either absorbed or have caused the fission or leaked from the surface of my device in that case. So you could see here that d over sigma a becomes an L squared, the diffusion area. You find that the sigma sub a here cancels out from that term, and it cancels out from that term. Let us rearrange another time to get some insight into it by dividing into L square phi. So the left-hand side becomes 1 over V L square sigma sub A minus an interesting term here, the second derivative of the flux divided into the flux. And that term is equal to K infinity L sub F phi minus 1 divided into L square. Now, notice now that we have a time-dependent term here, and then this term depends on the geometry. It is the gradient of the gradient, which is a Laplacian. In that case, you find that this describes how steep the distribution of the flux is in the reactor relative to the flux itself. That term here, del square phi over phi, appears in other applications, particularly structural engineering, and it describes how a beam is buckled, putting some stress on both its sides. You find that the beam buckles, and the term in structural engineering is the buckling. So in that case, we call it the buckling, and we give it the symbol B squared. But it depends only on the geometry of the reactor, as you could see here. So we are going to call that term the geometric buckling. Now that term on the other side here, L squared, is in terms of the diffusion coefficient and the absorption, macroscopic absorption cross-section. And we can calculate these two by the properties of the materials and their compositions, because we dealt with sigma sub F and sigma sub A and sigma sub S and so on. And in that case, the K infinity itself also is a function of the material composition. So we take that term and designate it as a buckling also, but only in terms of the materials. And we give it the symbol B sub M squared. So we call that term the material buckling, and we call that term the geometric buckling. Now we come to the very crucial step in our derivation here is that if we want a steady state, self-sustained chain reaction, that d phi partial by dt should be equal to 0, which means that in that equation, for a self-sustained chain reaction, I have to impose on the reaction that the material buckling here, B sub M squared, which depends on the material properties of the system, should be equal to the geometric buckling. And in that case, I get a steady state solution. And guess what? This is what we call the criticality equation in general. So in that case, the criticality equation, or the secret of the nuclear age, is very simple, is that the material buckling equation that we derived here should be equal to the geometric buckling that we have right here. So what does it mean for an engineer designing a self-sustained reaction or a nuclear reactor? Is that basically you have to match the material properties to the geometry that we have. If you have a geometry that's spherical or parapiped or a cube or a cylinder, then you have to match the material composition to the geometry if you want to have a self-sustained chain reaction. So this is basically what we call the criticality equation. It describes the steady state behavior of a nuclear reactor. We have to remember that the material properties are described by the infinite medium multiplication factor, by the fast non-leakage probability divided into L squared, the diffusion area, which is a diffusion coefficient divided into the macroscopic absorption cross-section. So it's a very simple situation here, really, considering the derivation that we have done for steady state. For a self-sustained chain reactions as engineers, we need to make that geometric buckling, the geometry, match the material properties. How do you change the material properties? You change them in the K infinity, the enrichment of the fuel, for instance, the how much moderator material do you have relative to how much fissile material. L square also depends on the material compositions. This depends only on the geometry, the slope of the distribution of the neutron flux, which determines the power of the reactor. All right, so it's very simple now. The material buckling should be equal to the geometric buckling for a steady state self-sustained chain reaction. Let's call it just B square here for simplification. And we can rearrange that equation that we wrote right here. Just use a scissors rule. And if you do this, you get that K infinity L sub F should be equal to 1 plus L squared B squared. And let's take the ratio of K infinity L sub F multiplied into 1 divided by 1 plus L B squared. And if it is equal to 1, that would be the self-sustained steady state solution. And that would be for just a critical system. Criticality here means that the system is just moving in a steady state because we assume that dN by dt is equal to 0. And that should be equal to 1, meaning that that term should be equal to numerator and denominator should be equal basically to each other to make it 1. In fact, the multiplication factor can be higher than 1. Say if you withdraw the control rods from the reactor, that number becomes 105 maybe. And if you insert the control rods, you can make it less, like a 0.8 or 0.9. So we are going to replace that 1 here by what we are going to call the effective multiplication factor. And in that case, we are going to rewrite that equation that the effective multiplication factor in general is equal to the infinite medium multiplication factor multiplied by that L sub F, the fast non-leakage probability, multiplied into 1 divided by 1 plus L squared B squared, which we can designate as a thermal non-leakage probability. So another way of writing the criticality equation is that the effective multiplication factor is the infinite medium multiplication factor from the 4-factor formula. We know how to calculate that, multiplied by a thermal non-leakage probability, 1 plus 1 plus L squared, which can be identified as the L sub thermal right here. And this term we'll see later can also be calculated and modified into the design. The important reason why we write the equation in that simple form here, that the effective multiplication factor is equal to infinite medium multiplication factor by the fast non-leakage probability multiplied by the thermal non-leakage probability, is simply to identify what is the situation of the system that we have on hand. If it is equal to 1, as we derived it earlier, this is what we designate as a just critical reactor, a reactor that can sustain a self-sustained chain reaction. If it's larger than 1, you find now that the number of neutrons start increasing in number, and that represents either an accident situation or a nuclear device, which is not our goal as engineers. So we have to keep that K effective really very close to 1, slightly above 1 to account for the absorptions in the control rods. And if we insert the control rods totally into the reactor, the number of neutrons that are generated from fission is less than the number that are absorbed in the field. So the system shuts itself down, and K effective less than 1 is designated as the subcritical reactor. All right, so these are two forms of the criticality equation now. And the question comes out, what is that phi here? What is that geometric buckling giving us information? What kind of information about the geometry of the reactor? Remember that we said that we have to match the geometry to the material composition, and that the geometric buckling should be equal to the material buckling. We identified that minus del square phi over phi as being the geometric buckling. All right, let's take that definition and use the scissors rule again, and you find that del square phi is equal to minus the B squared geometric buckling into phi. Oh, look at this here. It looks very much like what we did in the previous chapter in creating an analogy to the simple harmonic oscillator and to the tuning circuit in electrical systems. it was x double dot is equal to minus omega square x, right? Except that here we have a del square. That's a second derivative with respect to space, d by dr or d by dx, whereas the simple harmonic oscillator as an analog to our system is a second order derivative with respect to time. So in that case, we are going to use that analogy to our advantage. Notice it's a negative sign. And if when it was x double dot is equal to minus omega square x, the solution was an a cosine plus a b sine. And in that case, of course, it's oscillatory, call it if you wish. So oscillatory, you can call it harmonic or call it just cosines and sine. So instead of getting a cosine distribution oscillatory in time, cosine omega t, here we would have a solution that should look like oscillatory in space, sine of r or a cosine of r. So let's try to solve that system in the simplest fashion, in the same way as we did in the non-multiplying media in spherical geometry. So we can establish a comparison in that case. You'll find that the first step in the solution is that we write the expression for our operator here, which is a Laplacian. In spherical geometry, we said it is 1 over r squared d by dr, r squared d phi by dr. And in some other classes that you have taken in thermal classes, for instance, it was written in the format d squared phi by dr squared plus 2 over r d phi by dr. Either form is equivalent, as the same, just apply the chain rule of differentiation here, but d by dr, the first term by the derivative of the second, plus the second term by the derivative of the first. You get that form here. We are going to stay with that form, and that is equal to minus b squared phi. We are not going to repeat the derivation that we came through in the previous chapter when we took a point source in an infinite medium spherical geometry. The solution in that case, instead of being an a hyperbolic cosine, now has to be, because it's a harmonic system or a minus sign here, an a cosine plus a c sine o 1 over r. The 1 over r is typical of spherical geometries, so we adopt the same approach. We are not going to go through the same process as we did in the derivation for the flux in spherical geometry in a non-multiplying medium. In non-multiplying medium, remember, it was exponential growth and decay. All right, so here we have two constants of integration, the a and the c, and we have to determine them in the solution to determine what is that flux as a function of r in a spherical geometry reactor. If you take that solution and substitute it in the differential equation, that solution is satisfies the differential equation, so it's fine. This would be the mathematical approach to it, but engineers try to apply their mathematical knowledge to real life problems. So we start asking ourselves the question here, what if we take the solution at r is equal to 0, what is the cosine of 0? The cosine of 0 is 1. And if you divide 1 into 0, you get infinity. And that does not make sense because the flux we know, or a power in a nuclear reactor, cannot reach infinity. So that solution, even though mathematically correct, is not applied in real life. And since engineers are applied mathematicians, we conclude that in real life, that capital A here should be equal to 0. Hence, the solution for our neutron flux now in the spherical geometry should be a c, the second constant of integration, multiplied into sine, a sine curve r, sine of r divided into r, with the geometric buckling coming here as replacing the omega in the simple harmonic oscillator. In the limit where r tends to 0, you'll find that you have to take the apply L'Hopital rule to determine, because sine of 0 is 0 divided into 0, 0 over 0 is an undetermined quantity. We cannot say that it is 1. You know that from your algebra classes. So in that case, if you want to determine what is the flux at 0, you apply L'Hopital rule. And L'Hopital rule takes the derivative of the numerator, which is C, the sine becomes a cosine, and then you take the derivative of the argument here, B sub G R, that gives you a B sub G right here. You take it divided into the the derivative of the denominator, d by dr of r is 1. And then you take the limit as r tends to 0. And as the r tends to 0, the cosine becomes 1. So the phi sub 0 here, the flux at the origin, is equal to C multiplied into B sub G at the origin. So what does it mean? It means that I can substitute for the C here as phi sub 0 divided into B sub G. And here we have the distribution of the flux in our nuclear reactor if it is now a multiplying medium and in spherical geometry. It's a sine r over r kind of distribution. It looks very much like the cosine, but it is in fact a peaking at the center of the reactor where most fissions do occur, and phi sub 0 would be the value of the flux at the center. Notice that we are trying to solve for the neutron flux. It's the same as solving for the temperature, or the same as solving for the voltage in other applications. It's scalar quantity. It has no vectorial properties in general. But the solution is going to be a peak of the power or the flux at the center of the reactor. We are solving for the flux as a reminder, because now if you take the flux multiplied into the macroscopic fission cross-section, that's a fission rate, you multiply by the energy per fission, that becomes the energy produced per unit time, you get the power. So the flux here is a first step in getting the power distribution in the reactor. All right, so this is, we applied 2 boundary conditions here, but notice that you are still left with a B sub G, the geometric buckling here. So the question is, what is that B sub G? And in that case, we apply another boundary condition, in that at the at the boundary of the reactor, the neutrons simply leak out of the reactor a small distance. That small distance is going to be named D, or the extrapolated length. So at outside the reactor at a distance r, the radius of the reactor in the spherical form, plus that extrapolation length, the flux should be equal to 0. We calculate this from a more advanced transport theory as 2/3 what we introduced earlier as a transport mean free path. Some people even take it as 0.71 as an approximation. And if you apply that condition to the solution, the sine r over r for the flux at the boundary, then you'll find that that B sub G R sub EX, to make the flux sine r over r equal to 0 at the extrapolated boundary, that should be equal to n pi. You know that the sine curve, as it fluctuates or reaches a 0 at its poles, also 0 values, every pi as the angle of rotation. That takes the values 1, 2, 3, 4, 5. So the solution, in fact, is a combination of all the harmonics. However, we are interested in the steady state. So we are really interested only in the main harmonic that occurs at a steady state situation where n is equal to 1. So in that case, we can say that B sub G is equal to N1 here, pi over the extrapolated boundary of the reactor. And we can modify the solution for the power distribution in the reactor in terms of the flux as the initial value at the center multiplied into a sine pi r divided into the extrapolated boundary divided into, again, pi r divided into r, the extrapolated boundary. So it becomes a little more complicated, but nevertheless, you could see a big difference between our solution here in a multiplying medium and the case of a multiplying medium, and even a bigger difference when you have a vacuum. The flux in a vacuum from a source, capital S, was S over 4 pi r squared, if you remember, meaning that basically the inverse square law applied. When we took a non-multiplying medium, it was equal to the value of the, it had a term that had e to the minus r over the diffusion area. So it was a negative exponential divided into 4 pi d r. The one of the r squared in the vacuum case was substituted for by the diffusion coefficient in general. This solution is a spherical geometry. You'll find that in the textbooks, they like to simplify things. So they say, oh, okay, let us get the reactor power distribution in the case of Cartesian coordinates in one dimension. So in that case, the equation becomes simpler than the one that we have dealt with right here, obviously. But they consider the case of a semi-infinite reactor. Semi-infinite means that it takes a shape of a slab, a thickness maybe small x in the only in the z direction up and down, but infinite in the x direction, but infinite up and down. And that is not a physical situation. It does not happen in nature. We cannot have a semi-infinite slab. But let's just gain some insight into the problem on how to compare our approach here using a spherical geometry to what they do in the textbooks. Like take Lamarche, for instance, is one of the textbooks used in that case. The differential equation, because d squared phi over dx squared is equal to minus b squared phi of x. So the solution in that case is a simple a cosine plus c sine. We use there is not the 1 over r that appears in the spherical geometry. And in that case, we ignore the sine curve because the flux in that case cannot be 0 at the origin. So we drop the c, we say that the constant c is 0, and the distribution takes a shape a cosine bx. We apply the same argument that the flux vanishes at the boundary or the extrapolated boundary, and you get for the flux that it is an a cosine pi over a x. And the buckling in that case would be pi over a squared, whereas in our case is pi divided into the extrapolated radius square. Obviously, it's just a simple approach to look at it, but it doesn't apply to realistic situations. Another way to approach realistic situations is that we can think about a reactor not having just one single group of neutrons, thermal neutrons, but there are also fast neutrons existing in the process. So in that case, remember that we identified the thermal non-leakage probability as 1 over 1 plus L squared B squared. In the same way, we can deduce that the fast non-leakage probability is 1 divided by 1 plus tau B squared. Now, tau here, we have units of distance squared, but we call it the Fermi Age. It is some kind of historical, because when Enrico Fermi derived the equation, he thought maybe in terms of a diffusion system, and in that case, he described it with that tau. He gave it the terminology age, implying time. In our case, we know that has really it's a square of the diffusion area, not for the thermal neutrons, like in this case here, 1 plus L squared B squared, but for the fast neutrons. So if we rewrite that equation as K effective is equal to the infinite medium multiplication factor divided by that fraction of the neutrons that are not leaking as thermal neutrons multiplied by the fraction that of the neutrons not leaking as fast neutrons, we can get that form of the equation that now describes not just one group of neutrons, thermal neutrons, but also fast neutrons. Let's multiply those two terms in the denominator. What we get is 1 plus L squared plus tau, the Fermi age, B squared plus L squared tau b to the fourth power. Now remember that the buckling, the geometric buckling, is equal for the case of spherical geometry that we dealt with today, is pi over the extrapolation distance squared. So if you have a small reactor, definitely 1 over r squared is not very not significant. But if you have a large reactor, you take the radius here like 200 centimeters maybe squared. So that term here, the b to the fourth power, can be neglected relative to the b squared. So if we use only a large reactor, then that term can be dropped, and we are left with L squared plus tau, and this is designated as not the diffusion area. Now it's a square of the diffusion area of the neutrons at thermal neutrons plus their area of diffusion also as fast neutrons. We call this the migration area. And of course, in that case, b squared is the buckling, the pi over the extrapolated distance square. All right, so in that case, we can use either form of the equation. For a small reactor, as you can tell, we cannot ignore that last term here. So we simply use an L square for the combined equations in general. All right, so let us rearrange that expression for the buckling to determine the critical dimensions of a reactor. We suggested that the buckling, material buckling, b squared sub m, is infinite to k minus 1, and it was equal to L squared for a one group theory. Now here are using a two group theory or a modified criticality equation. So we have here the migration area, and that should be equal to pi divided into r extrapolated. So here we are taking the geometric buckling and equating it to the material buckling. Remember, that was the criticality equation. Let us use the scissors rules. And in that case, you can determine that r squared is pi squared m squared divided into k minus 1. And lo and behold, here, if we take the square root of the expression, then you can determine that the extrapolated boundary for a steady state system is pi, the square root of the migration area divided into k infinity minus 1. The extrapolated radius is the actual radius plus the extrapolation length. So if we subtract the extrapolation length here minus d from the extrapolated radius, you get the critical radius of the reactor. So you could see here that if we know the material properties, you know, the enrichment of the fuel, what fuel we are using, what is the proportion of fuel to moderator, we can determine the critical radius of the reactor. And obviously, if you know the radius and you have spherical geometry, you can calculate the volume. And if you take the volume, multiply it into the density, then you get the mass. And this is a way to determine the critical mass of a reactor that would make it self-sustaining. All right, so let us simply look at some data and try to plug them into an equation, the equations that we derived, and act like engineers now in designing an actual reactor, determining its critical radius, then its critical volume, then its critical mass. In that case, we need data for our calculations. One of them is the average number of neutrons per fission events. And we seek the data from the data warehouse. We mine for data as in the terminology of the information age. And we go to ANL 5800. This is Argonne National Laboratory Report 5800. And it gives us those values of the parameters that we need in our calculation. So for plutonium-239, you'll find that the number of neutrons per fission event is 2.98. For uranium-235 is 2.6. And also for uranium-238 is 2.6. Iron, sodium, and aluminum, of course, have no neutrons because they're non-multiplying media. If you think about the fission cross-section, you have to be careful here. You do not use the fission cross-sections for a thermal reactor, you use it for fast neutrons. So the microscopic fission cross-section for plutonium is 1.85, uranium-235, 1.4. And notice here that uranium-238 doesn't fission much at all. So it's really the uranium-235 is what we're fissioning and getting energy from in existing power plants. The capture cross-section is sigma sub c. The unit, as you remember, is the bond, 10 to minus 24 centimeters squared. And we get also the value of the transport cross-section to use in our calculations of the diffusion coefficient. And we are ready to solve the problem of to determine the critical radius, the critical volume, and the critical mass for a simple reactor system. And let us say it is an unmoderated fast reactor, meaning that it doesn't have a moderator. So in that case, it could be pure uranium-235. This would be a fast reactor. That's why we need fast cross-sections, because the neutrons have no moderator to be moderated. And in that case, we call it unmoderated fast reactor. Let's say it's unreflected. Why unreflected? Because if you add a material around the core of the reactor that reflects neutrons back to the reactor, the critical mass can be decreased. You're not losing those neutrons through leakage. So it's also bare because it doesn't have the reflector. So in that case, we use the data from a book on fast reactors written by Mr. Wirtz in the references. For uranium-235, he gives us the following data, that the density of uranium-235 is 18.75 gram per centimeter cubed. And if you are curious, go to the Wikipedia or the handbook of chemistry and physics. You'll find that the density of uranium here is very similar in terms of the density, very close to that of gold. So you can just get an idea about the density of that uranium. The value of nu sigma f that we need in our calculation is 5.3 neutron barn. Neutrons here, the average neutron produce an efficient event. Sigma sub f is a fast fission cross-section. Fast, why? Because if you don't have a moderator and you don't have a reflector, in that case, the reactor operates on fast neutrons. And something interesting here that to mention here is that in the comparison of Enrico's Fermi work and Werner von the Germans in general program during the Second World War, they never thought that they could have a reactor that operates on fast neutrons, whereas Enrico Fermi knew better about neutrons, and the United States really developed that fast neutron kind of a device, which became the nuclear devices used in the Second World War. The absorption cross-section for fast neutrons is 2.8 bonds. The transport microscopic cross-section is 8.26 bonds. So this is the data that is given to us. So let us apply our criticality equation. We said that the geometric buckling is pi over r sub c squared, and that is a geometric buckling, but we have to match the geometric buckling on this side to the material buckling, which is k infinity minus 1 divided into L squared phi. And we said that by using the scissors rule here, I can solve for r sub c, which is the critical radius, as pi, the square root of the L square f. Now, L square here is the diffusion area, which is really similar to the Fermi age for fast neutrons. It is not for thermal neutrons because, again, it's a fast reactor. Why are we using this pure sphere of uranium-235? So that we can compare our results to some experimental results and see whether our calculations make sense or not. So the r sub c here is equal now to the square root of pi and the square root of L squared. You can take L sub f outside the equation, no problem, divided into k infinity minus 1. So in that case, k infinity, as we know, is the four-factor formula. The L eta epsilon PF, and the L square here is equal to D for fast neutrons divided into sigma sub A. Now the data from the book by Wirtz for fast reactors is here, so we are going to substitute those numbers in the equation that we got for the critical radius. We need to determine what is K infinity, the infinite medium multiplication factor. It's a absorption rates in the field divided into the absorption rates in the total reactor, in the field itself. Now the field is just pure uranium-235. There is no moderator, no control rods, so that is basically sigma sub A divided into A. So we can say that F, the field utilization factor, is 1. And now we have K infinity, the infinite medium multiplication factor is eta epsilon PF. So epsilon, let's take it as 1, and the resonance escape probability also as 1, because we don't have uranium-238 there. So we neglect the fast fissions and the resonance absorptions. So the infinite medium multiplication factor is equal to eta. And that would be nu sigma F divided into sigma sub A. From the data of Wirtz here, nu sigma F is 5.29 neutron barn, and the sigma sub A is 2.84. So in that case, our infinite medium multiplication factor is 1.86. Remember, that applies to an infinite medium, but we have a finite medium in that case. So we are going to use it in our equation for the material buckling, the K infinity minus 1 in the denominator. All right, so that is for that material. This is a material property, enriched uranium-235. The macroscopic transport cross-section is capital N multiplied into the transport microscopic cross-section. Remember here, for that capital N, we have to use the modified form of Avogadro's law, not the mass here divided into the molecular weight. It is the density divided into the molecular weight. So the density of uranium-235, actually it's an alloy here of uranium-235 called oralloy. That is 18.75. Avogadro's number is 0.6 10 to the 24th. I approximated the mass of the uranium as 235. And in that case, you find that this number here, N, first the density multiplied into Avogadro's number, and then you have the transport mean free pass 8.46, 10 to the minus 24 to turn your bond into centimeter squared. So that 10 to the 24 and 10 to the minus 24 cancel out. And you could see why when I reported to you the value of Avogadro's number, I always wrote it as 0.6, 10 to the 24, because that plus to the 24 cancels with that 10 to the minus 24 here. And the macroscopic transport cross-section is 0.396 centimeter minus 1. We do the same thing for the absorption cross-section, and it comes out to be 0.137 centimeter minus 1, from which we can determine that the L square, the fast diffusion area, is a diffusion coefficient divided into sigma sub A. We calculated sigma sub A here as 0.137. We calculated sigma transport at 0.396. So the diffusion area is 6.1 centimeter squared. Now notice engineering wise that it is not a millimeter, it is not a meter. So the neutrons travel the square of 6 centimeters squared on average in that configuration that we are dealing with. So don't, if you are an engineer and you get a critical dimension in millimeters, definitely you think immediately that you need to correct yourself. If you get it in meters, you correct yourself. The characteristic distance here is centimeters squared. If you take 4, the square root of 4 as the L sub F, that's 2 centimeter, the average distance traveled by the neutrons. And if you take 9, that's the average distance is not 3. So the square root of 6 is between 2 and 3. So something between 2 and 3, let's say 2.5 centimeter is the average distance traveled by neutrons in that uranium-235. And you have to be consistent in the thinking about the dimensions are going to be in the centimeter range. So the critical radius, then, if we substitute in our k infinity minus 1 in the denominator, and L squared here, that's why we didn't take its square root, multiplied into pi, take the square root, you find that the critical radius of that uranium-235 sphere is going to be 8.4 centimeters. And from there, we can calculate, because we know the volume of a sphere is 4 pi, the radius cubed divided into 3. You find that that's 2,480 centimeter cubed. And how much material do we need to produce from that uranium-235 to reach a critical mass? We take that critical volume multiplied into the density, 18.75 gram per centimeter cube, and you get 46,500 grams, which is 46.5 kilogram of the material. Let us remember the radius here, 8.4 centimeters, and let us compare it to some actual experimental values here. An experimental experiment of uranium-235 was named Godiva. If you read, there is a song, in fact, about it that you can listen to on YouTube. Lady Godiva, in the history of England, was the wife of one of the princes or the rulers, and she went on a horse. She had long hair. She covered herself to protect his imposing taxes on his subjects, and she became a folk's hero. So Godiva went bare on a horse, protesting her husband's imposing taxes. And in that case, they named that experiment of uranium-235 Godiva. Look at the core radius, it's 8.71 centimeter. Our calculation gives us 8.3 centimeters. So it's a relatively good estimate here. If we use a plutonium-239 sphere, notice immediately that the critical radius is going to be smaller. So those countries that have been, and hence the weight, of course, is going to be much less. So those countries who are trying to build nuclear devices out of uranium-235 definitely can save lots of money by going to plutonium-239. In fact, the United States switched from using uranium-235, which means that the critical mass is 46 kilogram of uranium-235 for a nuclear device. It can be only 10 kilograms if you use plutonium-239. Hence, most weapons in the arsenals of nuclear states today are plutonium, not uranium-235. So you can say that the Iranians, with which we are trying to start a war with about their enrichment of uranium, as well as the Pakistanis, as well as the North Koreans, if they use the uranium-235, definitely they're on the wrong track. But, well, let them just be on the wrong track if it is a matter of weapons. If we switch in our future to the thorium nuclear cycle, with uranium to thorium being bred into uranium-233, oh, it's an even better situation. Look at this here. The core radius would be even smaller than the one that you'd get for plutonium or from uranium-235. So the uranium-233 is a very promising material for the future. Obviously, nuclear reactors are not just pure uranium-235 or plutonium-239. So you'll find that they started building reactors like ZPR-348, that's zero power reactor number 3. And you could see now that they used reflectors to reflect the neutrons around the bare core in that case. And in that case, you find that the critical masses and the critical sizes are reduced. For instance, with uranium-235, if you place 5.1 centimeter of iron you decrease your critical mass from that 8.7 to 7.4 centimeters in general. All right, so let us see how this is done. Now, this is, in fact, an actual picture. And the fascinating thing is that they're still making studying those experiments. So they are still refining the numbers that are used in the data calculations here. But this is an actual picture of the Jezebel experiment. You could see here that they were using rods here, remote control the kind of hemisphere on top and the bottom, and they were checking the critical masses, basically because you need to make sure that your data are correct in the calculation of the critical mass. And the approach to the criticality is done by bringing in the top hemisphere on top of those three cylinders in the center here, and then the lower one. A system of that in that configuration would be critical. We had a visitor from Los Alamos very recently, and basically he was reporting to us about still they're trying to reach better estimates for those data. So there is lots of uncertainty in those data, but back of the envelope calculation like we have done here can give us some very good calculations in general. So you could see here in 2016, they were still carrying out experiments on the X division at the Los Alamos National Laboratory. They considered that the critical mass of that plutonium spherical experiment, the Jezebel experiment, is 16.6 kilogram as a critical mass. Compare this to the 45 kilograms that would be for a uranium-235 sphere in general. The effect of the extrapolation lengths, if you have a large reactor, can be neglected because the reactor is not going to be those 8 centimeters of a pure system. If it is, say, let's say 2 centimeters for a reactor radius that is 2 meters in size, we can neglect that extrapolation length. So I'm going to give you an example in which I'll ask you simply to ignore the extrapolation lengths for simplicity. There is another example that I give you here about how these calculations are conducted, and I'll simply ask you to calculate the reactor core criticality for a exercises for the uranium-235 and compare it to the plutonium sphere in general, ignoring the extrapolation lengths as an assignment. All the theory that we developed is important, of course, to understand here. We have a problem with the video, it won't start. Okay, now it starts. So I'll give you a problem on which you solve for the uranium-235 and for the plutonium-239. And notice the difference between a multiplying system and a non-multiplying system. Okay, wonderful. I'll go to the chat room if you have questions, and we should be ready to go to our next chapter. Okay, no questions, so I'll start sharing the screen back again. And we are going to do something interesting here. Remember, we covered earlier the situation of the natural reactor, the Oklo phenomenon. And in the Oklo phenomenon, nature beat us in discovering fission. Of course, in nature, we mentioned that. Let's see what chapter it was. Natural nuclear reactor, the Oklo phenomenon. We covered that chapter, but we simply bypassed, intentionally waiting until the coverage that we did today on what happened at the situation of the Oklo phenomenon. Remember, we said that there were not just one reaction zone in nature where natural reactors occurred in nature. There were 16 natural reactor zones at the Oklo site. So the question is, and here is actually a picture of those reaction zones that happened at the Oklo mine. They were left here as some kind of geographical kind of curiosity for future studies in general. Let's look at what happened at the Oklo now with the knowledge that we have learned here. During the Oklo phenomenon in nature, uranium-235 concentrated in algae in an environment that was a marine environment where we had basically algae like kelp, and the water level also went up and down. And a most important factor in terms of the Oklo phenomenon was that the enrichment of uranium-235 2 billion years ago, before present, was higher than what we have today. Today, the enrichment of uranium-235 in uranium is only 0.72%, or we have 1 atom of uranium-235 per atom of uranium. But 2 billion years ago, that uranium-235 enrichment was higher. And the question is, how much higher was it? So we tried to figure that out by writing an expression for the enrichment at any time t in the past. So the number, that density of uranium-235 divided into the number density of uranium-235 plus uranium-238, which would be natural uranium, ignoring the number of atoms of 234 because it's very small. Today, it's 1 in 140 or 0.72%. Now, let us substitute for those numbers as a function of time, n sub 0 e to the minus lambda t. And let us, we know the decay constant for uranium, it didn't change since times past. So we can write an expression for the enrichment of uranium as a function of time. What we want to do is find out what is the enrichment at the time of the Oklo phenomenon. So in that case, we solve for N235 divided into N sub 0 plus N238, and we get an expression for it. And in that case, we can put this solution in a table. You're not required to look at learn the derivation. It's slightly complicated here. But at present, the enrichment in uranium-235 is 0.72%. Now, let's go into geological time in billions of years in the past. And the Oklo phenomenon, as far as we know, happened 2.1 billion years in the past. So I find that the enrichment of uranium at that time was 4%. And lo and behold, this is what humans have discovered in light water reactors. In light water reactors, the PWR and the BWR, the enrichment now is, in fact, in the range of 3 to 5%. Earlier on, 2.8 billion years ago, it would have been even higher, 7%. So today, we have only 0.72% that we are living with. And if we want to have natural uranium as a fuel, we need to use heavy water to decrease the absorptions in the hydrogen of the neutrons. So the enrichment level is one of the very important parameters for us to get a self-sustained chain reaction. We describe it as uranium-235 to uranium-238 ratio, or the fissile, because uranium-235 is fissile with 0 energy neutrons, to fission. Uranium-238 can only fission with fast neutrons, preferably in the range of 14 million electron volts. There was another important parameter that was existing at the time. The area of the marshes were consistently being flooded and then with water, and then the water receded and it disappeared. So in that case, the hydrogen or the water to uranium-235, in that case, the water acted as a moderator in the water in the marsh environment, the moderator to fuel ratio becomes also an important parameter in achieving a self-sustained chain reaction. Okay, wonderful. That means what? It means that we have to control the amount of fuel relative to the amount of the moderator present in our system. And that's still the case today. And that defines for us, in fact, that four-factor formula at the time of the Oklo phenomenon. So if you calculate that the infinite medium multiplication factor K infinity here as a function of the moderator to fuel ratio, you could see that as you increase your moderator to fuel ratio, you can increase your K infinity. And but up to a point, you see here it reaches a maximum 1.43, but too much water would shut down the chain reaction because the infinite medium multiplication factor also decreases. If you calculate the resonance escape probability, you'll find that the function of in the K infinity factor here, as you you'll find that as a function of the, if you increase the moderator, the resonance escape probability increases. But lo and behold, you find that the fuel utilization factor decreases. So now, if you multiply that P into F, you reach that maximum. And that's what I suggest. It's a design issue to maximize what is your infinite medium multiplication factor for the type of fuel that you have. You could see here they reach a maximum at a moderator to fuel ratio of 5, a resonance escape probability of 0.84, and the fuel utilization factor of 8.89. And you could see in that case that depending on whether the water receded in and out from the reaction zones during the Oklo phenomenon, basically the system went critical and then stopped and then became critical again and stopped, and hence it lasted for hundreds of thousands of years on and off situation. Another important aspect of the Oklo phenomenon is really the critical size of the ore and the moderator ratio. A very simple geometry consideration is the surface to volume ratio of a sphere. So if you take the surface of a sphere is 4 pi r squared. If you take its volume is 4 pi r cubed divided into 3. The surface to volume ratio is 3 divided into r. All right, so if in the case of a cube, it's 6 over a. So you could see here that the surface to volume ratio decreases as your r increases. Now the surface is where the leakage of neutrons occur from the size from the surface of a reactor, and the volume is where the nuclear reactions occur. And for this region, you find that as you increase the volume of your reactor, or the radius, in that case, the size, the surface to volume ratio decreases. Why? Many of the neutrons that otherwise have escaped would be reacting inside the medium itself. And that's why at some point you reach that critical mass by some kind of adjusting the nuclear reactions in the volume to the surface on which at which the neutrons are leaking from the system in general. And that's what the people at the Chicago Pi #1 in the first lecture that we had this semester were doing. They were adding layer upon layer of the graphite moderator and the uranium fuel until they reach that critical mass, which we spend time calculating today for a sphere in general. All right, and then an interesting aspect, of course, is that the Oklo phenomenon gives us an indication on what happens to the fission products, because we have to store them after we reprocess the fuel in our future and then return the waste back to the ground in the same way that we got the uranium out of the ground. So there is an interesting connection here that I bring to your attention to the Oklo phenomenon in terms of the criticality situation in general. All right, so here in studying transport theory. We covered today the one group reactor theory, and we connected it to the Oklo phenomenon. Now, nuclear reactors are not spherical only in shape. Nuclear reactors that we deal with can take the shape, in fact, most reactors, because of the mechanical design aspects, have shapes that are more like cylindrical. So the question is, how do we design not just a spherical reactor, but how do we design a cylindrical reactor? Or if we design like the Chicago Pi #1, maybe a cubical reactor, some reactor in the shape of a cube. In that case, we find ourselves having to deal with a Laplacian in the definition of the criticality equation that is not one-dimensional like in the case of a sphere, even though as we have done it for a sphere now, it was very simple. In the case of a parallelepiped or a cube, or in the case of a cylinder like the cylindrical reactor, you'll find that we are dealing now with a system that is three-dimensional in its shape. So here, let us take a parallelepiped core. A parallelepiped core can have, as a special case, a cube, but in that case, look at the Laplacian now. The Laplacian is not just d squared by dr squared, but now it's a Cartesian coordinate, d squared by dx partial squared plus d by c squared, d by dy squared, d squared p by dz squared. So it is now not an ordinary differential equation. It is a partial differential equation. And of course, some of you may have had classes already in partial differential equations. If you didn't, well, let's cover it here. But instead of bothering ourselves with a parallelepiped core, let us jump to the case of a cylindrical core and see what would be the implications in terms of the design of a cylindrical core, because that is the geometry that we use primarily in existing nuclear reactor. So in that case, as we suggested, if I have a finite a cylindrical core, the Laplacian takes a shape. One turn in the radial dimension of the cylinder and one turn in the axial dimension. So that would be the z dimension. Let me show it on a diagram here very quickly. So now the Laplacian depends on the height of the reactor as well as the radius of the reactor. If you do not have a dependence on the cylindrical angle, only those two terms in the Laplacian occur in that case. But we are dealing with a partial differential equation. You could see here now the partial derivatives here and there in the Laplacian. The way to deal with it mathematically is the method of separation of variables. If you haven't seen it before, be patient with me. You'll find in the end that's simpler than it looks like. And the method of separation of variables suggests that if the flux is a function of both r, the cylindrical radius, and z, the cylindrical height, then I can substitute for that function, which is a function of r of z, as a product of two functions. One is a function of r, and one is a function of z. All right, now, so let us get a solution phi of r and z and substitute it in that differential equation. For the first term, you'll find that that first term now, the z acts as a constant, and we have only a derivative with respect to r, and when we divide it to rz, the z and the z cancel. For the second term, the r acts as a constant, and it cancels out if we divide into rz. So you'll find that now we have two terms, one d by dr, r d by dr, and 1 over z, d squared z by dz. But that term depends only on z, and that term now depends only on r. So in that case, those partial derivatives disappear, and we end up with a total derivative. And if we solve for that function of r and for that function of z, and we can restore back the solution that has been separated into a function of r and the function of z. Now, since we substituted now the partial derivative into total derivatives, you'll find that you have a function here that's a function of z, and that takes the shape d squared z by dz squared is equal to minus delta square z. Oh, that is very simply the form of the x double dot is equal to minus omega square x. And in that case, the solution is very simple. It's in the z dimension. That z function is a cosine plus c sine. All right, cosine plus sine. So in the cylinder, you'll find that you get a distribution that is c sine plus c sine. The sine part can be immediately dropped as we did before because the flux cannot be zero at the center. So in the z dimension, you'll find that the solution takes the shape of a cosine in the z dimension. It's a little more difficult in the r dimension because we get that form of the equation, 1 over r, multiplied in 1 over r, d by dr, d by dr minus gamma is equal to a constant itself. Now notice that we suggested that in the z direction, it is as a substitution like the omega square in the simple harmonic oscillator. We called it delta square, and in the radial dimension, now we are going to call it gamma square. So minus gamma squared plus delta square is going to be equal to the geometric buckling. And we'll see later that the geometric buckling comes in and to represent the leakage of neutrons. In that case, the delta square represents the leakage of neutrons from the top and the bottom of the cylinder, whereas this term here, the gamma square, represents the leakage of neutrons from the radial direction, the surface of the cylinder in that case. So let us remember that B sub g squared here, the geometric buckling, is equal to gamma square plus delta square. Now, when we consider that equation, we run into a little unique situation because that equation is designated as a Bessel function. So when you get that shape here, you simplify it a little bit, it becomes d squared r by dr squared plus 1 over r dr by dr minus the constant gamma squared r. Now this equation is called a Bessel equation of order 0. And Bessel functions and Bessel equations always occur whenever we have any cylindrical geometry. So if you have, say, an antenna as an electrical engineer in the form of a cylinder, oh, you'll run into a Bessel function. If you have a rod, a heating rod in the shape of a cylinder as a mechanical or a civil engineer, then you'll run into that Bessel equation. So in general, then the solution is not going to be a cosine and sine. So let us look very quickly at Bessel functions. This is a general form of a Bessel function. And in that case, this is the Bessel function of order n. In our case, the order is 0. So we are going to drop that term. And the solution to that equation is equal to a constant multiplied into what we call the Bessel function of the first kind of order n. In our case, it's order 0 because the n here is 0 in our equation, plus another constant of integration multiplied into what's called the Bessel function of the second kind of order 0. And it's also named the Neumann function. If that sign here, the negative sign, is a plus, you'll find that that equation, in the same way as the simple harmonic and the damped oscillator, takes a different shape in terms of another Bessel function. We called it the modified Bessel function of the first kind of order n, and the k is a modified Bessel function of the second kind of order n. Well, it's a little looks complicated, but in fact, it's simpler than that. If you show on a diagram what those Bessel functions look like. The Bessel function of the first kind is shown here. J of order 0 is shown here. This is the x-axis here. You notice that it starts at 1. Oh, and it looks very much like the cosine. It comes down, 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 down here, crosses the x-axis, and then reflects back again in a decreasing magnitude cosine. You see here, it comes down here, but it does not reach all the way to -1. It's a lower magnitude, and then starts fluctuating around this line. The first zero, or the root of the Bessel function of the first kind of zeroth order, is here at that point, and you can read it here as 2.405. It is the same, it has the same similarity as the pi when the sine function gets its first root or its first zero at pi, or the cosine at pi, and then n pi, and so on. The y naught function in the second term of the solution looks like the sine curve, except that it doesn't start at 0. It starts at -infinity. It comes from -infinity and goes up and fluctuates on up and down. The Bessel function of the second kind, the k sub 0 comes from infinity, as you could see here. It looks very much like a decreasing exponential, and the I sub 0, the Bessel function of the second kind, increases up. So that corresponds to the x double dot is equal to plus omega square x, in that we get basically increasing and decreasing functions. In our case, the y naught and the y naught here function comes from, let's see, from -infinity. So mathematically, it's a correct solution, but it doesn't make sense. How can we get a negative number of particles crossing unit area per unit time? So we drop the solution, and we are left with the J naught function to represent the solution to the Bessel function, the Bessel equation that we had obtained here. This other equation would apply only when you have the plus sign in the Bessel equation. It would apply maybe to a shielding or a non-multiplying system if you have a cylinder to deal with in that case. So what's in essence then our solution, part of the solution in the radial dimension is a constant multiplied by the first Bessel function of the first and the second kind. And we drop immediately the one for the second kind. We say that f is equal to 0 because it doesn't make any physical sense. And the function r of r is now a constant multiplied into the Bessel function of the zeroth order of the first kind. Now remember that the 0 now does not occur at pi over a, like in the case of a sphere. The first 0 of the Bessel function, you have to remember that, is 2.405. So the solution in that case becomes the r as a function of r is a constant multiplied into j sub 0, 2.4r over r. And in the z dimension, in the axial dimension, it is pi z over h prime. It's the same as the cosine for a slab kind of function. And in that case, we take the r sub r here, the solution in the r dimension, multiplied into the solution in the z dimension. And in that case, it is a distribution that's a cosine multiplied into a Bessel function of the first kind of zeroth order. Remember, pi here is replaced by 2.405, the first 0 of that Bessel function. If we go back to the buckling, you find that the buckling now is that pi over h squared in the z dimension, in the axial dimension. And instead of pi, we have 2.405 divided into the radius in the radial dimension. And in fact, you find that the physical meaning of the buckling is it represents a leakage here from the surface of the reactor, and this one, in the top and bottom of the reactor in the z dimension. And this term here of the buckling represents a leakage in the axial dimension. And we can write now the equation for the flux as the products of the J naught function and the cosine function. In general, then we can construct a table here that what we solved for the buckling for the sphere is pi over r squared, geometric buckling, and the flux distribution would be a sine pi r over pi r. We consider the finite cylinder. The buckling is a combination of the axial leakage plus the radial leakage, and the solution is a j sub 0 2.405 r over r cosine pi z. And in the if you take the same situation without going through the details for a parallelepiped geometry, you'll find that the buckling has three components: one in the x direction, one in the y direction, and y in the z direction. And the distribution of the flux becomes a cosine in the x direction, a cosine in the y direction, and a cosine in the z direction. The parallelepiped here can be specialized into a cube. Since A is equal to B equal to C in a cube, then the buckling becomes 3 times pi over a squared, and the solution is a cosine, and a cosine. In that case, the A is replaced by A, the B by A, and C by A for a cube in general. In the textbooks, to make things simple, they try to use the parallelepiped geometry as a semi-infinite slab, which cannot occur in nature. You cannot have a reactor size go to infinity. So that's what they give us as a cosine distribution. And they use a semi-infinite cylinder. They say that the cylinder goes to infinity. It doesn't have a dimension in the axial dimension. So it they simply represent the solution as aj sub 0 2.405 r over r. We are here more realistic, because otherwise we cannot solve for an actual reactor, in that we are really considering a finite reactor. And we use a method of separation of variables. If you haven't had partial differential equations, that's a way to get introduced to it. And all that theory can be made meaningful if we consider now the criticality of an actual nuclear reactor, a pressurized water reactor. You'll find that for thermal design calculation, we are determining the height to be 3.7, about 4 meters. And in that case, we have to consider all the material compositions in the reactors. That's again, that's an actual reactor. The composition is H2O. The transport cross-section is given here in centimeter minus 1 for the hydrogen, the oxygen. It has cladding that's formed out of zirconium. It's a macroscopic cross-section here, as well as the absorption cross-section. There is iron, steel in the steel, the spacers. Then you have the fuel, uranium-235, 3 to 5% enrichment, and uranium-235. And then you have boron-10. Boron-10 is added at the beginning of the operation of the nuclear reactor, so that it burns out. As it burns out, it reduces the value of K infinity. Burns out means what? It absorbs a neutron, turns into alpha particles, and it disappears as the reactor operates, so we can increase the time of the reactor. Now, if you add all those transport cross-sections here for the different materials in the reactor core, you get a total macroscopic transport cross-section. If you add all the absorption cross-sections here in that table, you get a total macroscopic cross-section. And only the uranium-235 and uranium-238 have a nu sigma f value, and you add them together, that is 0.157 neutron centimeter minus 1 for the whole reactor. The diffusion coefficient is going to be 1 over 3 times the macroscopic transport cross-section. So you could see it has a value of 9 centimeters. And we can substitute for the infinite medium multiplication factor as eta epsilon pf. So that's nu sigma f over sigma absorption in the fuel. Let us take the fast fission factor approximately as 1. The resonance escape probability approximately is 1. And the F here, the fuel utilization factor, becomes the absorption in the fuel divided the total absorption. Notice that the absorption in the fuel and the absorption in the fuel cancel out here. So the infinite medium multiplication factor is nu sigma F divided into the total sigma sub A, which we know from here. And we know also the nu sigma F from there. So the infinite medium multiplication factor is 1.02 4/8. It's much less, of course. It's just incrementally larger than 1. So that reactor would operate very easily, allowing to the leakage by decreasing that one that K infinity into 1, and the system would be just critical. The diffusion area can be taken as d over sigma A. We have the d here calculated 9.2 centimeters divided into sigma A 0.15, so that's 60 centimeters squared, which makes the diffusion length as 7.57 centimeters. Again, this is not millimeters, it is not meters, so the characteristic dimension would be in the centimeter size. And we are ready with those data to calculate the material buckling. That would be K infinity as calculated, divided into L squared. It becomes 4.124 10 to the minus 4 squared. The extrapolation distance would be 0.71, the diffusion length. Notice here that the extrapolation distance is 19 centimeters. In that case, geometric buckling would be pi over the height plus pi divided, that would be that is the buckling in the z dimension, pi over the height of the reactor. We determined it to be 370 centimeter plus twice the extrapolation distance. We can ignore that extrapolation distance, and because 20 centimeter relative to 400 centimeter, the diameter of the reactor would be basically something we can neglect. So I'll give you the same problem by neglecting that extrapolation length just to make things simpler. So that is the buckling in the z dimension. The total material buckling is 4.1. So what is the buckling in the z now in the r dimension? It's really the total buckling minus the buckling in the z dimension, and we get in that case the buckling in the r dimension, in the radial dimension. And in that case, we know from the case of what we did earlier that that should be equal to 2.405 over the extrapolated radius squared, which gives me an extrapolated radius of 127 centimeters. You subtract from it the diffusion, the extrapolated area, and it gives you a 108 centimeters for a typical pressurized water reactor. You can calculate the critical volume. Now, it's not the volume of a sphere, remember that. It's the area of the base, pi r squared, multiplied into the height. So that's 13.6 cubic meter for the reactor. And that is the critical volume. If you know the average density, you can calculate even the mass for the reactor core. This is really typical dimensions of an actual pressurized water reactor in that case. We can also calculate the non-leakage probability for the neutrons, and remember the leakage probability. The non-leakage probability is 1 divided by 1 plus L squared B squared. So the leakage probability is 1 minus that quantity. You'll find that we are having 2.4% of our neutrons leaking from the system. I'll ask you to repeat the calculation here, just ignoring the extrapolation lengths. And in that case, you find that you are really dealing with an actual design of a nuclear reactor. You'll find that in that case, you are learning more than your corresponding nuclear engineering students, because at that level, they just stay with the textbook simple calculations of semi-infinite cylinder, semi-infinite slab, to avoid the idea of using a partial differential equation. So along this line, we reach the end of our lecture. Please work on the assignments. Everything that we cover today, including the assignments, will be covered by the test, and I hope that you can all ace it in that case. At that point, I'll stay in the chat room answering any questions that anybody has or wants to ask. Have a nice afternoon and a nice weekend, everybody. Thank you, Alvaro.
Thank you, Professor.
I requested that you be present so that you know how to help them in the assignments. Okay, thank you.